Howdy, my name is Matt Leonard. I'm the president of Texas Space Technology Applications and Research, TSTAR, because the rest of that's a mouthful. And we do a lot of different things in the area related to space and aviation exploration. So tonight wanted to advertise a little bit about TSTAR. I think I've talked to a lot of you before, but wanted to advertise a little bit about what we're doing, and this is one of the projects we're working on. Ooh, so that's a little hard to read, but we're engaged in bringing the business of space to Texas, evolving the space community from what it has been, a governmental run space community, into what it's going to be, a governmental commercial enterprise. And we're doing that in the Bryan College Station area because we've got a lot of unique things in this area that allow you to develop a robust space program that they don't have in a lot of other areas. Whoops, and we'll go forward now. So we've got a lot of different capabilities. I'm not going to go through these, but what we are doing is working on curriculums with different educational entities, A&M, Blinn, Bryan ISD, College Station. We're working on different platforms like Mission Control Center, those sort of things. Our business thrust, we've got a control center that we're building. That'll be a control center that can be used for educational purposes, for certifying people to be flight controllers, for demonstration purposes with commercial companies to understand the commercial space mission control needs, and with the government to do research on what the next control center might look like. We've got an unmanned aerial system that we're working on. We've been working on that with Ames Research Center and several others on how does the unmanned aerial system fit into the overall traffic management problem. And they're trying to figure that out, and so we're trying to help do that. And finally, the one that we're here to talk about tonight is our CubeSat program. And in that, we're working with universities and students and NASA and commercial customers and researchers. And the goal of this one is to provide a CubeSat service, which is a turnkey service. So CubeSats are a nanosatellite like Ruthie talked about. They're 4-inch by 4-inch by 4-inch. So they're very small so that the customer doesn't have to design a whole big space vehicle. But what happens is high school students or college students try to get in and build this, and by the time they get to the launch services, they're not designed the way that they should be, or they're designed differently every time. So what we're trying to do is build a turnkey system that lets you have a CubeSat that's just a basic platform, or all the way up to the Cadillac that can do all the different services that you want it to do: communications, power management, power distribution, power generation, and things like that. So that's what we're doing with what David's going to talk about. We're also going to be doing training and operations for CubeSats, and in educational interactions. We'll be working with high schools and colleges to help them get into the CubeSat environment. So that is really quickly, and I think I did stay under my 5 minutes, Dr. Morgan, an overview of TSTAR. And with that, I wanted to introduce David. David is in the master's program at A&M in mechanical engineering, and is assigned to the ESET program, where he's working on our CubeSat project. And I'll let you take it from there.
All right. Is this mic on? Can everybody hear me? Okay, you want me to talk into this mic? Can I carry it around?
Yeah, sure.
And let me get the other PowerPoint pulled up.
Do you want to pass around your CubeSat model?
Sure. Unless that's going to be a distraction.
That won't be a distraction.
It's a fun distraction.
All right, so there's the CubeSat. Of course, that's not a whole satellite, that's just the frame. But also, I wanted to know, can I walk around a little bit, or am I going to leave the frame? Because I have to show the video to my mom and dad, so.
I think you're good.
All right, I'll start off with a little bit about me. My name is David Malloway. I grew up in St. Louis, and I went to University of Missouri-Rolla for my bachelor's in mechanical engineering. I worked a few years, and then I came down here to A&M to work on my master's, also in mechanical engineering. So my research topic for my thesis is going to be a standardized CubeSat design and optimization. So today I wanted to go over a few things. First, what is multidisciplinary design optimization? the CubeSat design goals, and then finally demonstrate this optimization with MATLAB. So what is multidisciplinary optimization, or MDO? We're describing a system that has multiple disciplines and maybe very complex, like a modern car or airplane, something like that. And as we know that today's technology leaves us with experts who can only be experts in their one discipline and not a mastermind of the whole entire system. So if we look at designing a Ford GT, maybe we have artists creating the aesthetics, and we have aerospace engineers doing the aerodynamics. We have mechanical engineers developing the power plant, and we have heat transfer experts doing the cooling. Okay, but sadly we don't just have one really wise old man who can say, heat transfer, cooling, power plant, here's the design, right? So in industry, the current solution is to design in sequence and hand off the steps as we go. So there's one big drawback to having sequential design like this, and that's that each designer is subject to decisions made by previous designers. Let's say that for our Ford GT, we have goals such as a high maximized 0 to 60 performance. We have a visual pleasing car. We have good comfort. And then we're also subject to constraints such as 2 humans need to fit in the car, and it must fit in a physical envelope that's street legal, and it runs on gasoline because that's what we have available in the fuel stores, and it costs less than $500,000 so that all of us can afford to buy one. So, oops, let me go. Let's pretend that the feasible design space is the space that's full of designs that fit inside our constraints. And that's this green box I'm representing. And say for the artist, then this area outside of the feasible space is the designs that won't fit the constraints, such as maybe it's a really beautiful car, but it can't fit 2 people in it, or something like that. So they create their visual design and then they pass it on. Okay, and now it's even more restricted for the structural and aero guys. And they say, okay, let's meet the artist's requirements, and but we're going to have to make some modifications. We're going to drop the hood so it's more aerodynamic and we can meet this 0 to 60 performance. Then what happens is they have to tell the power plant guys, well, you can't put the engine in the front. It has to go in the back. And sadly, the engineers, their optimal, most powerful design was only one that could fit in the front, and it was sitting out here outside that design space. So they just had to go to the next best thing, and you no longer have an optimal design. And finally, we get to the cooling feasible design space, and it's all messed up because the engine is hot and it's in the back, and the cold air is cold and it's in the front, and they have to route hot boiling pipes of water by the passengers to cool down the engine without burning the passengers alive. And then they go over budget because they had to spend so much on this insulation. So I also had a quick story about my time at Toyota. For about a year, I was in the Toyota engine calibration group. And I want to get a show of hands. Who thinks that the calibration is the first step in designing a vehicle? All right, you were very smart. How about somewhere in the middle, maybe? Wow, okay, you're very, very smart. It's dead last. So for the Toyota Tundra, they tasked the team of calibration engineers with making the Tundra so that it will not stall when the customer fills the fuel tank full of E85. Now, E85 is a completely different fuel than gasoline altogether. But we don't want it stalling because we want to deliver a flex fuel vehicle. That's what all the competitors are giving. So the calibration engineers said, all right, we're going to use the fuel sensor to sense how much is E85 in the tank and how much is gasoline, and then we'll send that information to the injectors so we know how much fuel to inject. And they came back to us and they told us, well, the hardware design engineers decided to cut costs and there is no fuel sensor. So that created a hairball where the calibration engineers have the Toyota Tundra performing experiments inside the engine continuously and trying to guess what kind of fuel is in the truck. And mind you, the constraint on this design was the customer can never notice that the engine is behaving oddly at all. So we have challenges with sequential design. MDO, on the other hand, is a simultaneous design, and it's only made possible because modern computing allows us to make models that are fairly accurate, and depending on how well you build them, to model a design. And it's made with an optimizer as a program that manipulates a design vector that's describing all the parts of the design. And it's also working to optimize the objective function, which may be that 0 to 60 time. And it's checking for feasibility continuously to make sure you're not creating an impractical design that cannot be made. So the optimizer also deals with the constraints and the parameters that are fed in. I'll tell you a little bit more about how parameters work. But these are all just models that'll give you finally an optimal design configuration. So now we can talk about what is a CubeSat. And just so happens that it's a multidisciplinary complex system. So it's a perfect candidate for MDO. And like Matt said, it's carried on by a rocket. It's a very small satellite, and they get launched into low Earth orbit. And they orbit the Earth for maybe a couple of months before they gradually fall back towards the atmosphere, and they combust into dust and whatnot. So the purpose of the CubeSat is to equip it with some sensors or some experiment, and then send this data back to Earth before it blows up. And but before they can carry out their purpose, they need to have some base functions such as electrical power, attitude sensing, communication, structural system, and attitude control, possibly if you want to be able to flip it around and point your solar panels towards the sun. And the background image that you can see a little bit maybe, these are a whole flock of satellites called doves that are triple-sized CubeSats made by Planet Labs, who hope to deploy this whole entire constellation of satellites that can take a photo of Earth every 24 hours of every square inch of Earth and make it publicly available as well. That would be pretty cool, I think. So my design goals are create a framework that can be re-optimized for different missions, adjust the configuration as the project moves forward. For example, if boss tells me we are going to use these batteries, they're no longer a variable, they are a fixed parameter, then I set that as a fixed parameter and we can continue to optimize everything else. Then finally, take heuristic data from previous CubeSats. Because I don't have advanced physical models of every different element in my design. For example, I haven't modeled each thruster, but I do know that there are previous CubeSats that use this thruster or that thruster. They have name brands and part numbers, and they achieve this performance. So I will just put a data point for each one, and then I at least have some accurate data to work with. So this is how the MDO problem was formulated for the CubeSat. We have objectives of minimizing the mass and minimizing the cost. Because if we minimize the mass, that leaves also a smaller volume that we use with our components, and that leaves more volume available to the customer to implement some kind of experiment. The parameters, there may be over 100 in my program, I haven't counted them, but they're things like the mission duration and the power of a solar panel. We tell that if we install a solar panel, just one of them, it's going to get 2 watts of power. So these parameters can be changed, but in general, they're fixed for one run of the program. Finally, we have constraints such as the power required by all of the electronics on board for the whole entire mission duration must be met by the batteries or the solar panels in combination. The structure bending stiffness must be sufficient so that the structure is strong enough, basically. And the propellant is sufficient to push the satellite in a spinning motion to adjust the attitude all the way through that mission. Now we have a design vector of 6 different design variables that I've included. And of course, you could make as many as you want. But the first 3 are strictly discrete. We have a propellant type. These are different gases. We have a thruster type, and these are little electromechanical devices. And we have the structure material, physically like titanium and steel and aluminum. And each of those has a whole bank of characteristics that are loaded into the program so that it's going to be able to calculate the parameters correctly, or the outputs correctly. Then the next 3 variables are how many solar panels, how many batteries, and what's the width of the structure. So, and these can actually all be treated as continuous, even though there's no such thing as 1.5 batteries. If we allow it to choose 1.5 batteries, then we'll know that the program is doing something intelligent and not just always going to 1. Okay, so here's basically the flow diagram of how the program works. You input some design vector that quantifies all those variables from the last slide. And then the 3 modules, structure, propulsion, and battery/power, are computing basically the outputs and the objective function respectively. And then finally, all those outputs are put together to give you the mass and the cost of the satellite. Right here in the middle, we have a feedback loop because the propulsion module might say, oh, you've chosen this kind of thruster. It requires this much battery power. And then the batteries will be adjusted to accommodate that, and that's going to change the mass of the satellite. And then the propulsion is going to have to come back and say, oh, now we need to add a little bit more propellant so we can push this big fat satellite around. So there's a fixed point iteration method to make sure that those 2 converge. And then finally, we output a mass and a cost. Now you might ask, how does the design vector get chosen to go into the whole calculation? Well, there are 2 major ways to determine the design vector. Basically, you can have an algorithm that's heuristic, meaning that there's some amount of randomization involved, or you can have a type of algorithm that's solely math-based, and we call it a gradient-based algorithm. And they both have their strengths and their weaknesses. But I want to kind of use an analogy that our design space is this egg crate up here. I wish it showed up a little bit better. But let's say that on the egg crate, the highest points are the highest mass, and the lowest points are the lowest mass. And we want to explore the design space and reach the lowest mass, and finally say that this is our optimal design. Well, the genetic algorithm works basically in this way. It takes one design vector that I input, it could be anything, and then it's going to evaluate the objective function, find the mass out, and then it's going to create maybe 10 or 50 offspring that are slight mutations where it's treated that vector as some kind of gene. And it's going to mutate all of those children in a slightly different way, and then it's going to reevaluate all of those. And it's going to find out which one's the best. It's going to pick the best child, and it's going to create another generation of more mutations. And it's going to keep on jumping around until it basically improves for each generation. Now, it's possible that one of the children, or all of the children in some generation could perform more poorly than the parents of that generation. Maybe some of you have experienced this in real life. But luckily, the genetic algorithm, it remembers the very best design so far, and then if the following generations are not better, then it's going to store that one and it's going to keep it. The only problem is it's good at finding the largest pocket or the biggest valley, but it's not good at finding the very lowest point in that valley because there's always some small random change. There's not really a direction to it. So that's when we get to SQP, sequential quadratic programming. It's a gradient-based method where basically it takes your design vector and it measures the designs that are similar in all different directions by basically perturbing all the other variables, and it's creating a slope basically what's the gradient of the design from where I'm standing, and which direction do I need to go to get to the steepest descent. And then it very quickly converges on the lowest pocket in that design area, the local design area. The weakness of SQP is that if you start it somewhere like, do I have a laser? Yeah. If you start it somewhere like up here, it's going to get caught in the local pocket. It's not going to find the global minimum. So for the CubeSat, I've combined the two methods, used the genetic algorithm to pick the bigger discrete variables, and then finally refine the design by letting those variables be passed into SQP and let it refine the design to the global optimum. And with this method, it's fairly repeatable, not 100% repeatable, but I think very good for having randomization involved at all. So let me see. You don't get the demo yet. Basically, I just wanted to show you that I created this output, this graphical output, to be able to check the inside workings of all the modules to say, well, if we get a mass at the end that's like 931 grams, that sounds like a reasonable design. I don't think it's going wrong, but let's check inside all the other modules. What are the parameters that have been calculated, and check that those are also reasonable, because that's basically been a major way I've debugged the program and found out that maybe the structure was stuck. It was stuck on one value, and then I was able to fix that. So let's see if MATLAB will cooperate with us. Okay, do you want me to run the program with the default parameters, or should I tell it that the solar panels, instead of making 2.1 watts, they just make 0.1 watts? Well, let's have a vote for the first option. That's 2, 4, 5. Okay, and then for the second option, you guys want me to screw up? Okay, well, I think it might work anyway. We'll see. 0.1. So remember, the optimal for the previous design was 921 grams or something like that. All right, we have a genetic algorithm. This seemed to get stuck kind of quickly, but it found something. I'm going to minimize these windows. And I'll share this with you. Can you see the blue dots at all? So this time the program only went through 60 generations, and it looks like after about 20 it was unable to find any children that have improved from the previous generation. So it just kept that for long enough that it said, okay, I'm terminating myself because I'm not improving. Not terminating the satellite, but oh, we do have some 0.034. Let's see what we have from the other window. So this says, this is the SQP function. It's only done 3 iterations to do its job. It's much faster. And it basically, the end result was 3.5 kilogram satellite. So when your solar panels don't make very much power, you need more solar panels and more batteries. And specifically, you need 4 solar panels and 10 batteries, so it's a lot heavier. So I guess it kind of works. That's confidence for you, right? Kinda, I guess. And that's almost wrapping it up. Okay, so that optimization was based on mass only, just one parameter. We weren't including cost, but in real life we need to include cost as well. So what we have is a Pareto front that we can create. That's this graph here is based on 2 factors. We have cost on the bottom, mass on the left, and our ideal point is this star. It's basically the tiny mass and the tiny cost, so it's great. But that's not feasible. Feasible is up here where things are not as nice. And we can use an adjusted weighted sum to calculate this. The adjusted weighted sum means that we consider our objective function to be the sum of the mass and the cost. We start with fully placing importance on the mass. We run it, and then we gradually place more importance on the cost, and we continue to run it until only the cost is what matters. And we create a whole bank of all of the designs that are truly optimal, but it depends on what you want. So then I can go back to Matt, and I can say, well, if you want to be a cheap guy, the best mass you can achieve is 1,300 grams. But if you want to be, the top of the line best satellite that there can be, then we're all the way down to 800 grams. So, and then we have like kind of the design variables here. You can tell that they're all made of different things. They're entirely different designs, but they're all optimal. So that pretty much concludes my presentation. I do want to give a special thanks to Dr. Allaire, that's in my mechanical department, taught me everything I know about MDO. Dr. Joseph Morgan in electrical systems. He's supporting my research. He's my co-advisor. Of course, Matt Leonard with T-STAR, and then some NASA personnel that are helping us with some, just provide data and support to our designs. So, and I think now I have time for questions, maybe? Right here.
Are you looking at just cube sets that take up a single cube, or like the dubs you were showing that are multiple?
I believe in the future we want to be able to have a capability for 3U. They call those 3U satellites. They're 3 times the size. Of course, once you have that size, you can fit a lot more electronics and stuff. Yes, Paul?
Parametric variations, the dependencies, what is it? Is it like an equation, or is it like you have to do computations which are more detailed from a CAD design? Or so what is the dependence between mass and, let's say, power and all those? What is the relationship? How do you get to?
Basically, we're trying to meet the constraints. We don't try to maximize the so, for example, the constraint was we need to have enough power. Now, since that's a constraint, it could be made into an objective, but it's a constraint, so we only need to meet it. If it was an objective, then they would try to make even more power than you need, right? So once the constraint has been met by, say, adding this many batteries and this many satellites, or sorry, this many solar panels, then measure the mass, because each battery and each solar panel has some mass. Then measure the final output and check if your design is better than the last. Does that kind of answer it?
Right, but so you're assuming that those relationships are being assumed. So you have a kind of relationship assumption.
Yes.
In your
There are many, many assumptions, and this can be vastly improved by getting more data compiled and also just finding more components and with their data that goes along with them. So we have more variety to work with. Yes, sir.
As you add different constraints, obviously, the graph you showed was just cost and mass. It becomes much, much more complex, and your optimum solution is not feasible in the real world because it wasn't along that line. So my question is, how does that compare to how it's being done now? By identifying what the optimal solution is, does it allow the decisions to be made to say, okay, we're going to have something that's not optimal, but have to be better than how it's being designed now?
You're saying, can you set the goal, realizing that optimal is impossible, set the goal to just be improvement from the current strategies?
And is it?
Yeah, you can definitely do that. Of course, I've never created an optimization that was parallel with somebody else in a design department. So I can't say mine's better or not, but that's where the research is going, and that's why Boeing actually created a swept wing body aircraft. That they're always making trade-offs between, okay, we want passenger capacity, we want fuel economy, we want cost, we want like 4 other things. The swept wing body was done using this method, and it was improved like 20% on everything. There's only one drawback, and that was that it was intrinsically unstable, and it could only be flown by a computer, and humans don't trust computers, so it's not very sellable. Actually, one more drawback is that it's harder to assemble because our assembly lines are already ready to build normal airplanes, and this one was a weird one. So.
Any other questions?
Thank you.